again. Just do the usual, share some links. Let's go share on Twitter. And then let's not share on LinkedIn today. I think Twitter is the crowd we're after. That's where all the homies are. Anyway, to jump back in where we were, so like quick recap what we did last week. I'm also just jumping in, like I haven't worked on this throughout the week. I have Banana I work on and other projects. But I did go and clean up the notes. So to really just recap in like 30 seconds, we kind of figured out like what exactly is the internet. Well, the internet's a TCP IP protocol. Like that was the first real definition of the internet, is like it was rules for how to send data between computers. And that lets everyone agree on a shared way to send and receive data. Hey, random sequence, welcome. Yeah, so basically last time we figured out what the internet was, kind of went through this like what makes the internet, went down a deep dive into like signal theory, providers, URLs, like just all this different stuff. And then we tried to scope out like, okay, if we're gonna build the internet, like what does that mean? Because this could easily be like a 6-month project if we don't scope. We basically broke it down into 2 parts. So the first part is implementing the TCP IP protocol in a language of our choice. I think we're going to use Python. Yeah, so we're going to use TCP IP in Python. And then the second is we need to actually send data to another computer. And technically we could use the same computer, but I just don't count that as internet. Like if you're not sending it to another machine, like are you really doing internet? You're just mocking internet. And so today we're going to drill into this first chunk. Which again, I've never done this before, so it's still going to be a lot of exploration. If you're familiar with these concepts, would love your input, because we can kind of learn and explore together. And I imagine some folks that tune into the stream probably know TCP/IP much better than I do. But the point isn't to know everything; the point is to learn it. So that's what we're doing. And again, a quick recap is like wrote out this very high level like the 3-step process for TCP. It's called the Three-Way Handshake. Again, TCP just means like, I think transport, something protocol. Let me actually get the definition right. Let's not make up definitions. Transmission control protocol. Okay, so it's basically defining how 2 computers shake hands before one sends data to the other, vice versa. And it establishes a 2-way connection. So sometimes they use a different terminology here, but basically it's called the SYN-SYN-ACK, where like synchronize and acknowledge. And so one computer sends this like synchronize request. The other machine says, hey, I acknowledge your request, and I'm also requesting to connect with your computer. And then the other computer says, yeah, that sounds good. So it's kind of like 2 people saying like, hey, do you want to go to McDonald's tonight? And the other person's like, yeah, I want to go to McDonald's. Do you want to go to McDonald's? And they're like, yeah, I want to go to McDonald's. And everyone's like, hey, let's go to McDonald's. So that's basically how TCP handshake works. We started implementing it in Python here. So this part, I looked back, I opened this code again, and I was like, oh, this is embarrassing. Because I went from like high level to start implementing, and I'm like, oh man, these interfaces are probably gonna suck. I'm gonna have to like redefine a lot. But basically trying to make a state machine. And then the other thing where now to like jump right back in, where I wanted to kind of resume was one question that came up while I was doing other stuff in the week was basically like, where do sockets come in? So like if you look up Python socket programming, right? There's this like, I found that there was a guide on like how to do sockets, and I'd found resources like this often. And I was trying to figure out like, well, where does this connect with TCP IP? Like, am I missing something? Because see, they talk about TCP sockets. So I wanted to like, I didn't deep dive it yet. I was waiting until stream, but basically, I'd like to understand what this is, and build a minimum. I think today like a minimum interface is, I want to go right down to the driver level, as low as I can go before hardware, and I want to be as like narrow as possible so we can actually get that depth. Like I don't want to be implementing just high level interfaces all day and never actually get substance. But yeah, this is the first thing. Like I just don't, I've worked with sockets. So my high level understanding is like, yeah, there's like this kind of routines for sending and receiving data, and sockets they seem like an abstraction above multiple protocols, because I think you can have UDP as well. Yeah. So there's UDP, TCP, and it's like TCP sockets. So I basically want to understand that this is part of our abstraction. Like if ignoring this is dumb, like from an engineering side. Yeah, I mean, this makes a lot of sense. TCP. So basically, endpoint, communication channel, the channels used to send data. So it's local or over networks. So it's abstracting away this notion of the underlying hardware. So it's above hardware. It's actually very similar. Yeah, this electrical analogy makes sense. That you like plug in a wall socket, and then the electricity just goes somewhere else, but like you don't really care how or where or what. Let's see. I think the part I'm curious about, so if I go into here, is sockets defined? Yeah, it sure seems like it is. It's part of the TCP nomenclature, even in the 80s. So yeah. So they use the word socket. So this is like old school. This isn't some new abstraction. So it sounds like we should be aware of sockets. So a connection is specified by a pair of sockets, a local socket. And so this is where like IP addresses and everything start coming into play, from my understanding. I just need to like understand more like what this is. Yeah, okay, layers. The internet does not strictly obey the OSI model. That's funny. Let's have a model and not obey it in any way. Yeah, this is exactly the question I have. So where do sockets come in? Like it seems like this weird middle abstraction. So we got application layer, we got TCP, UDP, so it's in between. So it seems like a wrapper around TCP, essentially. Like, so if I think about it, like my understanding is server client is a little bit too abstract from a code perspective. Zoom in a little. Oh god, it's a little too much. But so if I did like a low level abstraction, it would be like SYN, IP, and then it would be like ACK. So it'd be like sending a SYN request, waiting for a SYN ACK, sending an ACK, like doing all these like handshake things, and then like specifying the IP address. There's probably, I imagine with TCP implementation, like a bunch of other stuff around like packet ordering and things like that. And then like with sockets, it seems like it's more just like S equal like connect. You define a connection and then you like send data like that. So it's a bit of a simpler wrapper around TCP. And the reason that seems clear is because it's doing TCP and UDP. So it's a wrapper around the transport layer, essentially, which makes sense. But that would mean that it's not necessary in order to say we've done the internet. Like we don't need abstraction layers around different protocols for our MVP. We sure do if we want to support different protocols, but sockets versus file IO. Nice. Okay, I'm just gonna keep reading through this. They're using terms I know, so it seems like we're on the right track. Yes, it seems that there's two types: file sockets, like just writing to a local file, and then this thing called a socket, which I still don't fully understand like what it is. Okay.
Coffee?
Oh, I've got a coffee. Thank you, sir. I've got 2 coffees. I'm stacked with coffees.
One for the TCP and one for the IP.
Yeah. Three-way coffee handshake. Okay, so I think, like my gut tells me we can just jump in and be like, scope the heck out of this, but like basically I feel guilty saying I'm implementing TCP IP and we're not dealing with ports, sockets, and IP addresses, because I think that's a pretty important part of the protocol. So I'm gonna spend some time just kind of grokking that. Set of calls. Let's actually save a link to this document. Ports. So sockets are identified using the IP, something, and a port number. TCP sockets. Ports are objects. Okay, so port just represents, I think, a connection, which makes sense, right? Like if your computer could only connect to another computer, like if you could only have one connection on your machine, that'd be kind of dumb. So you have ports, and you can have like different applications, different your mail server and other stuff concurrently. So I get that. Socket functions like connect, accept, and bind. Nice. So we got TCP server defined here. Bind, listen. So I guess socket, this bind thing is basically the three-way handshake abstracted into how they define creating a socket. So like another way to do it really ground up is just like sockets in Python. If we just look at like what does a socket library look like? Get a better understanding here. I don't want to read like the raw docs, but this is sufficient. I mean, this is pretty clean. actually love this. I'm just gonna try using this. See, like, just make a dummy file. Sockets.py. I think I have Vend set up. Cool. No matching for socket. Come on. Come on. Can I just run this? Is this like Python 2? Might be. Yeah, this is Python 2 because they're the print statements don't have the Python 2 supports prints with no brackets. Python 3 doesn't. Connection refused. Okay, cool. I mean, that's simple though. We've already got this connect thing. Basically, okay, I know our port's wrong. I know our host is wrong. But this is nifty because socket is essentially this wrapper around TCP in Python. And so if we drill in and be like, well, what does connect look like? So receive is just getting data from another socket. Let's connect. Do they have like the implementation here? They're just pointing me at. It's probably just binding around C, as Python does. Doesn't do much by itself, does it? Got it. Okay, so simplest level, if we're using sockets, we have a connect function. We can do receive. We can just like start getting data. I'm really curious like what this receive function, like how this is implemented. So I'm gonna look into that quick. So here, they're not gonna show. Buff size. Let's see. Damn, getting into Chinese sites. That's how you know you're in deep. Okay, so I think for scope's sake, we can ignore sockets here. We're gonna hard code a port. We're gonna pick a port. We're gonna pick a IP. So we need to know how to define an IP. And we need to know how to define the port number that we're listening on in both sides. But I'm just gonna, to establish just a bare minimum connection for the requirement we have, we don't need to have all these different ports and stuff. I feel like that's gonna be a whole different, that's a whole different stream, like being able to do multiplexing for applications. So I'm actually gonna spend just like a few minutes deep diving the original proposal. I think that'll help close some of these loose ends. Okay, we don't need intro. How long is this? Just to make sure, is this gonna be like a, that's not crazy. Let's just do top down, skim it. So we're gonna see some intro stuff, some philosophy, and then functional specification. This is where it really matters. Opening and closing. All right, let's just see like what we learn here. I think this is better than all these like geek for geek tutorials. So I know the motivation. We know we have OSI model. This is actually like pre-OSI model. They didn't even have an application layer because nobody was building applications because there was no internet. It's kind of funny. So it's amusing that they're like, well, something above TCP is going to be a higher level and things will happen. And then people are like, yes, I will create Facebook and Reddit. And then the government's probably like, what have we done? Process communication, yeah. Interfaces. Yeah. So it connects with the IP protocol, the internet protocol. So it's using files. So for us, like sockets are a nice abstraction around basically the IP address and like keeping state. To actually maintain state, we'll just use file system, which is exactly what I was intending at the beginning. The interface between TCP and low-level protocol is essentially unspecified. There's a mechanism whereby the two levels can asynchronously pass info. Got it. Yep, we're using files. That's the... Yeah, and so TCP needs to handle a bunch of broken stuff. Data transfer, reliability, flow control, multiply. Okay, so we're gonna do basic data transfer. Reliability will be a thing that comes next. I think flow control is gonna matter, so like the ordering. What is in each direction? Okay. Cool. Got it. Flow controls for bandwidth and not ordering. So I think the basic data transfer is just how do we send packets? And then multiplexing the single host to use TCP simultaneously. Ports, yeah. So ports, sockets, there we go. This answers the question. All that kind of confusion. So the network and the port form a socket. A pair of sockets identify each connection. Okay, that's pretty clear. Actually just gonna like save that blurb. So that's sockets. And that's part of multiplexing. We don't need it yet. Yeah, binding. Binding is a whole thing. Let's just assume we've done binding. Certain status information for each data stream. We're gonna have one data stream. Each side. Cool, okay, let's drill in a bit more. Yeah, gateways. Yeah, this makes sense. A packet, data of a transaction between a host and its network. Yep, a packet is a small chunk of data. Nothing surprising there. Internet IP module associated with each TCP provides an interface. The internet module packages TCP segments, routes these datagrams to a destination. Internet module. Cool. Yeah, operating systems. This is cool. All right, let's get down more into the interfaces. Interface provides for calls made by the user on the TCP to... Okay, so the TCP interface provides an open and closed connection to send or receive data to obtain status. Cool. So we have an application level, gateway level, network level. So I'm curious about this. So it's basically saying we need some simple functions to support. Open, close, send, receive, or obtain status. Okay. Seems like they're binding sockets pretty close with TCP here. So they're saying like open is like one of the fundamental operations to support. And then in open, we need to do foreign socket port. Passive open requests. Cool. So there's open, close, send, receive, status. That's what we need to support. Obviously, we can just do open first. So we're getting back into the handshake, but a stream of octets. Cool. Some principles. Nice. All right. This is where stuff matters. Now we're getting into functional specification. Imagine this is where most of our energy will be spent. TCP segments are sent as internet datagram. I don't know what that means. The heck is a datagram? Cool. So it's like a packet. Is this a packet or is this something else? What do you mean by datagram? Self-contained message sent over a network. Okay. There was the falling here. All right. New words. Header and payload. Yeah, it's clean. Do we still use this term, or is this just like people in the 70s talking about this? An IP packet is an example of a datagram. Okay, got it. Cool. Yeah, data. Okay, so a datagram is a broad name for sending data, is a logical chunk. A packet is a subset of that under the IP definition. It's an IP packet. Cool. New words. This is to be analyzed using host level pro. I need to know. So okay, TCP packet. How big can a TCP packet be? Okay, cool. So so basically I'm looking at this, I get that the header is up here. So here's our header. That's standard size. But then data, it's like, what is that? Like, do I send if I'm sending a cat picture, do I send 50 TCP packets or TCP segments, I guess we're calling them? Or do I just send a huge payload? Urgent pointer where it's going to get down to data. Where's data? Come on. Are they going to define the data section? No operation. Did they just skip how the data is defined? Padding. So padding is the next. We talk about padding. Yeah. So then, cool. And now what? Segment variables. Okay, so they're calling it segments. Send sent, send received, establish. We'll even define the state machine for us. Yeah, this is nice. They gave us the state machine. Nice and simple. So we were even being more, look at this, like they make it really easy. Like once you have the specification, you're just like, I gotta implement this thing. Okay, I still don't, like they're leaving me in the dark here. How big can a TCP segment be? Yeah, like what is this? So it is setting dependent. Okay, this makes sense. So maybe TCP doesn't care. I need to figure this out because this is like, I mean, this is clearly part of the, okay, key part of sending data is to know how much you can send. TCP length is the TCP header length plus the data length in octets. Okay, so let's just go, we're gonna have to, I mean, the next step here is this is kind of like the grunt work, but like we gotta do it. We have to define this struct. And so we need to understand like what all these windows are, and we need to be able to create, we need to be able to have an interface to like very cleanly read and write over this. Like this is where like bug city is gonna be. If we don't read and write this structure correctly, we're gonna like get the wrong bit sent, and like we have off by one errors, it's gonna be just awful. The number of indicates where the data begins. The TCP header is an integral number. I'm just gonna, yeah, sequence number. So when we're doing SYN and ACK and stuff, we're going to be setting these bits. Yeah, makes sense. They need some way to actually know when we get an acknowledgement from the other machine, which packet, like which request is it talking about, especially when we're doing multiplexing. 32-bit words in the TCP header. Data, okay. It's an integral part of the 32 bits long. Reserved for future use. Control bits. Synchronized sequence number. Cool. We don't really need a checksum. I think that's just for like reproducibility. Like it's just security measure, my understanding. Just double check actually. Like, what is a checksum? so much of this stream is just, what does this mean? Detecting errors that might have been introduced during its transmission. Oh, okay, so it's not data integrity. So it's integrity, not security. So I guess they're doing something to be like, oh, if bits got flipped somehow, this checksum is like a small, it's like encoding, or is it encoding? I think it'd be encryption technically. It's changing this input, like the data format, into like a small bit string. And then if any of the data changes, that checksum, that hash, that number, whatever, will change. And because it's 1-to-1, I imagine. I mean, we don't have to deep dive that, but basically it's helping, it's a quick way to tell if the data that's been sent is broken or has changed in some way, instead of having to do a linear pass over the data, which is nice. Less compute. TCP must options, okay. Whatever y'all say, gov. So segment size. I have a feeling this seems like the thing. Yeah. Cool. So we have high-level calls wrapping around a state machine that is defined here. So you have all this stuff. Instead of the user having to manage this, we just do it under the hood. Every octet has a sequence number. What is an octet? Does that just mean like 8 something? 8 bits. So it's a byte. Why do they call it an octet? Come on, lads. Sure. Okay, it's just naming. So TLDR, octet and byte both mean the same thing. Octet literally says 8 in the name, oct, and so it's less easy to goof up. Versus a byte apparently had a different definition. Somebody said byte was 16 or something, and that confused the hell out of the industry. Now everyone's like can't agree, and they're like, we must have another term. So octet is a good, you can't really confuse it. Sequence number space, yeah. A typical kind of sequence number comparison which TCP blah. Receive acknowledgements. The following comparisons are needed to process the acknowledgements. Blah. Acceptable ACK. Let's just skim through. Just like details. Just blah. Initial sequence number selection. Again, we don't really need like rigid. Like these are all questions that we will ask and then just kind of pull the specification when we need it. We don't have to read it top down. Clean as heck, bro. I mean, this is so nice. We just know exactly how it's done. Okay, I'm still stuck on being like, how big this TCP thing is, like this packet, or not packet. TCP segments are sent in a datagram. That's that. The header contains the data. Maybe they have better on Wikipedia here. Yeah, some color. So the header doesn't seem to have the data defined in it, which makes sense. It goes options padding. Yeah, options padding, and then the data is going to be sent elsewhere. I don't fully understand that. Like where do I send the TCP header is sent here. Options. I get that. Do they define it, at least in the specification? Like, do they use a word like payload? No. So I think it's called a TCP segment. Yeah, header and data section. Nice. Now I think we're getting the words right, so we can zoom in. Segment structure. Okay. The header contains 10 mandatory fields and an optional thingy. Data section is the payload. There we go. There's that word. The length of the data section is not specified in the segment header. Okay. That explains why this is confusing the crap out of me. Hey, Flightless Ferret. Welcome. Okay. So they don't specify the length. It's specified elsewhere. It can be calculated by subtracting the combined length of the segment header. This is the header. And IP header from the total IP datagram length specified in the IP header. So TCP doesn't care about your payload size. All it does is it's breaking stuff down into IP packets. And then those IP packets have a size length. Cool. So I guess the part that I'm a little fuzzy on here is the actual, so I get the handshake. It's like, cool. The handshake is all headers. We're just sending like specific flags to maximum segment size. Yeah. But then it's like sending data. Data transfer. I feel like these universities publish some pretty nice PDFs. Okay, so we have some rules to make sure we send stuff in the right order. Okay. Cool. So basically, if we just jump right into the code, I think we have enough information to continue on this. So like, we're going to implement the state machine, which is going to be wrapped around these simple open, close, whatever requests, and we're slowly going to define a TCP segment. As we go. Like, basically, I'm not going to sit here and just like go through the whole packet definition one by one, like one bit at a time. We're just going to be like, all right, it's just bits. Who cares what they are? Let's implement the state machine. I think the one thing that's just like irking me is to see how to send data. So where is this? Listen, received, sent. Yeah, so I guess there's a handshake. some interfaces. So now we're getting, okay, now we're getting, I'm trying to remember actually, like, what's the, so I know C++ and Golang lately. Haven't used Python much, and I don't want to take Golang and just like butcher Python with it. So we know Python has, like, what's a nice way to implement an interface basically in Python? So there's structs. So basically we need an interface though that's going to define send, open, close, send, receive. I don't know how to spell this. Status. So we need some sort of thing which is like our connection. We're just gonna call it a connection. And I know like Python has, right, like we have classes, and then we have, does Python have structs actually? I can't even remember. Let me check. Now we're getting into some of the implementation, but I'm trying to remember, how does Python do structs? No, that's C++, yeah. I was like, wow, that's so familiar. I know exactly what this means. And then I was like, not Python. So defining interfaces. Duck typing, no interface. When it's received, EIV, thank you. Flightless, sorry. So we're basically, okay, so there's no interfaces, there's no strict enforcement of anything. So everything's just classes, I guess. Okay. Okay, everything's just following a class definition. And then duck typing, to double check my understanding of duck typing is the whole, if it supports the methods, like you just check, does whatever object you've passed in support calling this method on it? If it does, like it's the type you need. You don't actually care about the explicit type definition. That's because Python's dynamically typed, from my understanding. So we can clarify a couple of those things. Yeah, dynamic typing. Yeah. So you just literally say, if it has a talk method, you can talk. Cool. Nice. Is it actually spelled this way? It is too, Jesus. I think I spelled received wrong probably half the time. Because I'm just so used to the IE pattern. Anyway, so we're gonna have this thing called a connection. I think we use uppercase in Python. There's like an init, host port, yeah, we can have that. And then we're gonna define some, yeah, open. Oh, so now anyone here who is familiar with GitHub Copilot, yeah, I before E except after C. Yeah, now I'm seeing it exactly. So basically, check this out. So we define open. Copilot's just gonna like try to like generate a full number of things. We're not gonna use it, right? Because it doesn't make sense. But it's familiar with the notion of like sockets being part of a connection, and that I'm writing an abstraction, and it's gonna like, watch, look at it. So it knows that the next thing's close, like because I wrote this comment up here with the order. So it's actually pretty insane when you see just how quick it can generate stuff. But if you go down here, send. So it's wrapping around sockets. I don't know. I think it's pretty bonkers, personally. I'm probably not going to implement it this way because, again, like Copilot isn't the best at design decisions, but it's pretty incredible at giving a structure. So we go down here. But like, what do we need next? We're going to have receive. It just blows me the hell away, honestly. It just makes coding so easy. It's like, so yeah, again, like I think sockets make sense as a wrapper. I personally want to be a level of abstraction lower. So Copilot's recommending that I use sockets internally in this connection. I'm actually doing the other, where like they've got their abstractions backwards. Like connection is going to be used within sockets. Like I'm going to implement socket eventually, and then socket is going to be like calling new connection and stuff like that to do the handshake and all that. Or connection actually might just be a socket in this case, technically speaking. Like if we're going to pass in a port and a host and we're doing the handshake, it's basically a socket. So Copilot's being silly. Let's just hard code. Let's think of these other things. Again, like they're recommending a bunch of code. I don't know if I agree with it, right? So I'm not doing a connect in the init function. I'm not doing this socket stream stuff. Yeah, I'm removing these socket calls entirely because like this isn't a wrapper. And then I think what I would like to figure out here is like what order we want to do first. So from an application level, I suppose there will be state stored inside here because connection is going to contain a state machine. So for example, when we do open, when we call open, we can look here in this, where's the state diagram? There's a really nice, I wonder if we can find a better Tcp handshake state diagram. I know so there's two different diagrams, right? There's the syn-ack diagram, but then there's like, no, how's it actually implemented here? Looking for a nice fresh diagram. Looking for one that resonates with me. I for some reason really like DARPA's. I like this ASCII one, to be completely frank. Like it's clean, doesn't spook you out with like weird arrows. I just wish I could find one that's shaped like that. Like I guess this basically. Can I open this? I guess this one's okay too. So where's open done though? That's what I'm trying to figure out. So basically we're gonna call open and then do a bunch of state transition stuff. And then we have these two sections. So there's like, there's termination. Like each of these have a different way of interacting. So I'm just trying to see how do we implement a state machine beneath this in a way that isn't dumb. Let's just use this one. Yeah, just for sake of, I'm trying to make sure this is actually the right thing though, so we don't goof ourselves, because this is talking about like, this is very explicit, like open, close, and then these other diagrams have like passive open and like weird stuff, like timed waits and like, which isn't part of the specification from my understanding. Yeah, I think the safest bet is to use the literal diagram here. I think it's worth trying to grok this. So like, and this is just kind of like a technique I've learned from hitting my head against design long enough, is like, I rather use a obscure but original source than a simpler, easier to understand but wrong source. That'll bite us way more down the road if there's like just this weird new language that's introduced, or like the design's incorrect. If it's a diagram wrong, just made by like undergrads doing like an OS project, they're like, oh, I will like include my own custom diagram, and then forget to include a state, and then just somewhere across the world, domino effect, that just ruins my string. It's closed, active open, creates TCP and send. Cool. So I think the order I'm gonna implement these is open, send, close. No receive, just open, send, close. On the other machine, we're gonna need listen and like, I guess technically we're gonna mock both of these on the same machine. So we're gonna have something like, let me see here. So server, again, all this state is gonna kind of just get dumped into here. Okay, again, I'll clean that up, but yeah, sending. So before we were just like coding all the states into like two functions, which fully aware that's like just dumb. Like that's not gonna, like that, you're not abstracting away like the socket logic. But basically client's gonna have this thing, new connection. We're gonna do like host port 8000, which is default. And then, so we're gonna use this connection defined below once we flesh it out. And then we're gonna do something like con dot open, yeah, and I think this is gonna be the handshake. Like this is, I'll actually make this delay. So we could make it an async, like a status flag. Like we could have a flag basically and then check the status of it. Well, there's no new keyword in Python. Yeah, you're gonna see how shitty my Python is. I was seeing this error too as it comes up. This is what I get for going with like language switching while doing something completely new, but that's the fun of it. I think my defs are right. What's wrong with this? Oh, it's just indented? What is it? Does I have a problem with my, I think this is good. I need this to return, is it just upset? Oh, it's because of this, I bet. Yeah, cool, anyway. So we have connection, we're gonna have an open. We will just like, I guess we'll define a result. Yeah, I put a return, it's all good. I'm gonna put result in open just in case it fails. We'll call it success. So true or false. And then we're gonna say like if success, like we'll do some error handling to not be just barbaric. We're gonna do connection.send. I'm gonna send yo. The modern hello world. Yeah, and then like close. Cool. We don't even need a return here. So like that's basically that's what's going on. And then in the server we're gonna have we're gonna also define connection. I don't actually know, so the host is gonna be different. We can actually just be like, let's just simplify this. I think they're both called hosts, right? Yeah, it's just host. So the client doesn't, we don't need host client because it's just like, it's a host. We know what we're calling. Keep it simple. We'll just call it just for server IP. We're gonna call connection. We're gonna do con. And now, so the server is gonna be interesting. So it's simultaneously listening for a connection and receiving data, right? So we need to almost have like, this part's kind of neat. Is this like a callback, like an async? I think it's listen. So, okay, like I get that technically speaking, both of these are supposed to be listening and connecting, but I'm trying to simplify the state. It's like just conceptually to be like, if you can go one way, we can go both ways, but like, let's separate the logic for the sake of just like getting data sent. I don't think the server needs a host IP. Well, so my understanding is like the client and the server are different machines. Both are going to need an IP, right? So to establish a handshake, both of them have an address that they're aware of. But I'm not. So if it's the case that the server is listening, right, which I'm trying to figure out right now, the server is listening for a request, and then it just if it listens, it gets a request that then says, hey, here's my IP, then maybe the server doesn't actually need to broadcast its IP. Because it's implied the client would already know it if it's sending a connection request, right? But yeah, I mean, that's something I'm sure I'll figure out. You sound like you're a step ahead of me. But I'd make the argument that both machines will need to have an IP of some sort. To be recognizable. So I guess we're just doing like con.listen. I really don't like that these are blocking calls. Because, okay, like technically, like obviously the listen should be a background thing. Again, I'm just making it like super blunt. We can optimize it all and just like make stuff background processes once we get there, but let's just make it super explicit. I don't even think we need timeout logic. Like we're basically gonna say the server just sits there and listens for a connection. That's it. And then once it gets a connection, it's going to be data equals con dot. It should be received. Yeah. I don't even know if we want a payload size, but this is basically what's going on. So that's like roughly the structure I'm seeing here. And I'll check the diagram a bit to see if we're using the terms right. So there's close, open. I mean, I'm using the exact terminology that open, send, receive, close, abort. I think what we're missing here is the listen. Like I've included this listen thing, which I don't know if that's how the server is gonna actually receive a connection. So I think I need to understand that a bit. Did they use the word listen in here? Yeah, they do. So there is a listen state. I don't know what they're talking about. Yeah, there's a whole state for this. But I think the point is that listen isn't a method, or it's not a function. It's supposed to just be a state that the server is constantly in, and then the listener is going to be like polling to check if there's a file that's been written with like a synchronized request. And then it'll move away from that. But like I'm basically wrapping it in listen though, like just for the sake, which might be I'm trying to think of like how would they do it elsewise. And I think a great way to do this is to look at sockets. If I just look at a socket tutorial, like how do they initialize a client and server? Particularly the server. They have a listen function. So I think I'm thinking about this pretty darn smart, if you ask me. You define a socket, you say bind. I don't quite know what bind is. I assume that's just like making resources, like sanity checking that your host and port are available and you can actually expose them before you do a listen. But then it's just listen, yeah. A bunch of state. Cool. I think it's okay. So I just wanted to make sure I wasn't like deviating from the specification. I can't wait until this stream hits Hacker News and people just come in and start just roasting me. Like it'll be a really clear day and night difference. Like people are just like once I start seeing the complaints that I'm not using Rust, that's when I'll know. Cool. So I wonder if we can mock these right now, just for simplicity. Technically, these are blocking calls, so we need to actually put these in sub-processes, which I will do. Let me see, there's a way to do this in Python. Python has a sub-process library, if I recall. No, okay. I want to do run function as sub-process. Yeah, and I can't, so Python has Python has a weird way of doing threading. It has this like interpreter lock. So like, if I recall correctly, Python blocks threads and it gives you this false sense. Like you have concurrency because you're switching between threads really fast, but if you have one thread block, it's not actually doing them at the same time. So basically it just like, you can lock up your threads and then it having a really slow execution. I'm not sure if that'll affect us in this case, but I think since the server, how I'm implementing it is just like busy polling, and it's not explicitly telling the thread that it needs to wait, it'll block entirely. So like the client server won't work. They won't run in parallel. So we actually have to use sub-processes. And processes, those can run separate. So again, like thread is like a individual unit of execution within a process. And then a process has its, like each process is like one thread, but they're running separately partitioned in user space. So classic Python gotcha. I'm just trying to avoid it this time, but I bet I will hit it again. This guy's post reminded me of it because people are like, how do I not do this with threads? I think this is right, multiprocessing. OS fork, there's like an easy library for this, come on. I'm pretty sure it was this popen. Yeah. I don't know why there's a Q. Yeah, this is the approach I recognize. I don't think we need a queue. I don't know why they're using that actually, but I should probably. We do need a main, so we'll go down here. What is queue supposed to be doing here? So, oh, is queue just gonna order the results? I don't think it matters. We don't need a queue. Like we don't care about the results ordering right now. We do care about creating sub-processes. So don't need this. Get rid of that. Get rid of queue. Server and client. So we're gonna have a server. Also, where's this code completion? Like, why is this all dark? This is getting, it's because of the Yeah, that'll do it. A while true. Let's just clean out. Nice. Okay. Server. I mean, we'll just have process. There's a way to do this where you can have multiple processes before you call join. I guess it's just start. Because the whole point of process join is it waits, and like if I'm blocking that, eliminates the purpose. Yeah. So my understanding, if I just do S server and then client, look at that. See how majestic that is? Like it just knows what I'm trying to write. Can't get over how dope that is. No arguments yet. This is probably gonna be needed eventually, but let's just like keep it simple. S dot start. Let's start the server first, yeah, and then the client. I mean, I guess we can wait. I really don't. Yeah, because we can't have this process exit if we don't wait. Like if we don't do a join. Yeah, I know we're doing multiprocessing in Python. I know it's garbage. Yeah, I was thinking the same thing. To stand back, it was very hard for me not to do this in C++ because like deep down, I'm like, I've already done sockets in C++. I know we can do it. But then I was thinking like, well, the syntax complexity across multiple hour streams, and the fact that like, I think most people are exposed to Python and then they're gonna see C++ and get like hung up on like I don't know, vector, like they're gonna get like stuck on this shit and be like, oh, what are all these colons and like IOStream and all these like libraries, whereas Python's just like, it's a process. Here's the inputs. It's easier. So, but to be clear, if I was doing this for like an actual like for a company, like if we're actually building this for real, we should probably use C++. Yeah. So we got that, and then let's just do server.join. So this is going to make sure we wait until both server and client exit. If they don't, something's goofed. Boom, boom. Technically, these can be in different files. I'm kind of like, okay, I'll just say it verbally if this is confusing to you. Like, again, I'm skipping over stuff like processes, like which you haven't built with processes before, it might be confusing. Essentially, this process call means that this function, server, right here, is gonna run as a separate process. It's gonna have its own process ID. It'll be running completely independent of this main script, so this main.py. So what we're gonna end up doing here when these 2 lines, or when these 4 lines are done, is we're gonna have the main.py process, and then we're gonna have a server and a client process. Each of them are running the same file, but it's really just important to note that like I didn't put these in different files just because I didn't feel like it, but like it can be confusing if like server is not running from main.py in the same file. Like it's not like you can debug and go, oh, process started, where are we in this thread? It's gonna be a whole different application that's just running this one function. Yeah, so anyway. And if we really want to test it out, actually, I'm wondering if both are piped to standard out. Where are we in server? We in client. I want to see if it, just real quick, pipes output correctly. It's bare minimum. Because this is going to be the workflow we're using for a while here. How do I run this in Python? Is it like that? Yeah, now we're gonna start getting hit with like all the debt I've introduced with my shitty code. Okay. Yeah, we gotta start cleaning stuff up now. It's unacceptable. Let's just do this. By clean up, I mean comment. Ha ha ha. Sick. I imagine there's gonna be a few cycles of fixing syntax errors. Yep. Still 44. What's wrong with this? Oh, these returns, man. Good. Are we happy? Are we happy, Python? I have returns from all my functions now. Nice. That worked. Also, this is weird. The debugger did stop, which concerns me because it shouldn't, because it's a separate process, unless the debugger attaches to all downstream processes, which is like super dope. Let me try this. That's wild. See, doing this in C++ would just be like setting up this debugger with like LLDB and stuff. That's a nightmare. Look at this. So it actually knows that it's a subprocess. Okay, so now I have it visualized for you if you're curious. Like, we have a separate call stack in each of these processes. They're completely disjoint from here. So when these exit, it'll unblock the joins. But yeah, beyond that, this is a separate environment. It has its own, there should be some way of seeing this in local, right? It should, yeah. So the variables defined in each of these processes are completely different. I'm trying to prove it out. Parent ID. Yeah, so they each have different parent IDs. And then the main file shouldn't have any scope because it's not defining anything. So each of the downstream processes do. That's cool. I'm pretty thrilled by that. I didn't realize, like, okay, for context, if you've debugged multi-process applications, it's usually like there's a whole day spent just setting up your debugger, which again is why I didn't use C++, because I know that that's a thing. And I was like, I don't want to spend a day of my life setting this up for a stream. And I don't want to do it during a stream because that'd be dumb. So, yeah. But then the trade-off is you get multi-processing, which sucks in Python. And you get the global interpreter lock. It's the price you pay. Anyway, it's cool. We got nice clean interface. Am I using Git right now? I probably should be. Yeah, I think it's time to do a commit. It's just like, let's make some logical checkpoints. I don't think we need any of these other files. We care about VS Code. Again, I'm using Brev for my, this whole environment is a Brev instance. So it just spins up with all my code completion and stuff. I don't have to use my local computer, but I don't have to go elsewhere. And then VS Code is the IDE, so. I apologize, this is called Internet from Scratch -CPP, and it is not C++. You can tell how much I wanted to. Yeah, that's dope. Let's just drill in. So what I want to do next is I want to mock these individual calls. By mock, I mean they should all print stuff, and they shouldn't break. So I should be able to run this, put a fake delay. So like, for example, I mean, this, I don't really care about this, the state stuff. I'll keep state defined here. It's kind of ugly. Client. Let's just go through each of these functions and be like, what do we want to do to mock it? So for open, let's just put a time.sleep. Yeah. And then let's do a print saying like, in open, let's do connection, established connection with self.host. So again, I know we're cheating. I know we didn't, but we're just we're getting like what this will look like once we have the state managed. This will probably be the first and hopefully not the last time you see the print statements work, because once we start implementing a state machine, bugs will come up, shit will break. I haven't even thought about how to unit test on this level. I just assume people don't. Like, to be honest, like I think once you're down in the networking level, unit testing is like that's an application level thing. But we at least want good debug statements. We're going old school. Trying to open connection with host. Let's make it a bit longer, just to make it feel authentic. And then we're gonna go here and we'll be like connection.close. I don't see how close could fail. Yeah, I don't think the close function could actually bail out, because the client could stop connecting. Like there's no like way the server's like, no, you can't, and then it's like, okay, I will maintain this connection. It's like, no. Payload. So send is an interesting one to me, because sending the payload, and then what we're gonna do is like break this into packets, right? Right. Yeah, seeing the idea of how to test this is interesting. I think the big thing is, so what's really fun in doing a live stream, I'm noticing, I highly recommend others try it if you haven't done a live stream of this. It's a very different dev experience. And the reason is mainly, you know that you can't get stuck on things, right? So like, if I'm doing dev not in a live stream, right, my inclination is like, oh, I'll just figure this out, and then I'll spend like 4 hours trying to set up testing and being like, but then in a live stream, it's like, okay, here's the goal, here's where we are, and I'm like, how do we scope this? So it's a very like aggressive scoping. I would watch your live stream. I don't know who you are, Flightless Ferret, but I would watch your live stream. Anyway, split. For context, I'm doing this based on memory, but like, I'm pretty sure there's a way that you can have like self dot, like a private method, and then it'll know. I think it's like an underscore is just like a naming thing, I recall. If I'm butchering that, apologize, but basically this is a private field. This isn't, you shouldn't be calling this from outside of connection. Just to make sure I'm not making up design patterns. It's been a while, so let me actually just check. I believe it's right. Yeah, cool. So like in it, I don't actually know the double underscore, but I know there's single and double. Private method is double. So what are the single ones? I know that there's 3. Let's just be consistent then and make it double underscores. Okay, got it. Yeah. I don't know why they're not using a single one. I'll use double on one side just to be consistent with Geek for Geek, who assume knows Python better than I do. But yeah, basically it's private method. Split. I think that's how you do a for. Yep. Sending packet. We're gonna have a 1 second delay per packet. Got it. Okay, so double underscores mean, so if I did something like split, like this, then I could call I could do something like, and then I could do split, right? I could call split around it. Or I could do con. Yeah. I think that's my understanding. That's cool. Oh, not exactly. Is that incorrect? Now I'm curious. I'm gonna figure it out. Got it. So it's an interface. Okay, now I know it. Now I'm tying it in. So by interface, you mean Python objects have this ling. There's like if an object implements that, Python will let you call length on it, right? But it's not agnostic. So you can't just define some random thing and then call it. Like I can't define like foobar with double underscores on both sides and then just call it foobar with my function. But with ling it works because Python supports that, and then get item is specifically for square brackets. So I can't just define like overloaded type. Okay, cool. That makes sense. Cool. Let's split this into two. Just like I want to actually have sending packet. Eventually I'm gonna have like header information in here, but basically send payload. Receive. Let's make these fast. I before E, except after C. Let's keep it consistent. Status, I don't really care about. Or honestly not even implementing it. So let's just get rid of it. See what breaks. Oh god, these breakpoints. That's what breaks. Okay. What do you mean there's no open? I defined it. Oy vey. It feels something dirty about using an uppercase. This is just like naming convention, but like, I don't know, there's something, uppercase function name, I can't do that. I'm sorry. I don't care what the standard is in Python. I'm not uppercasing my methods. That's ugly. There we go. Like if Python encourages you to do that, that's sad, but. Connection object has no attribute listen. That'll cause problems. Yeah, I should probably support listen. Oh, did I define it and it's just uppercase? Like this? No, we didn't. Yeah, I think the standard's lowercase. Like, I just don't know a single language where they're like, yeah, uppercase at the beginning of your function. That's barbaric. Oh, God, of course, Microsoft. We got, indentation. waiting for connection with this. The funny thing is like figuring out when to return from these. So like, okay, again, I'm just mocking it. So like time.sleep, let's just say it's 5. It's gonna be really dumb. Let's do 3. Received. So handshaking, there's gonna be some weird handshaking stuff here. Like all the SYN-ACK logic's gonna be right here. Because like basically this listen and open are gonna be the two big logic chunks. Send is just like send a payload. That's not extremely complicated. The other cool thing is we need to have an interface with drivers at some point, because like right now I'm implementing it in Python, right? And it's like all process level, but somewhere we need to be sending packets to a Raspberry Pi. For context, for those who weren't on the last stream, got a Raspberry Pi here. We're gonna be actually building like the Wi-Fi adapter. Like we're going right down to the hardware, and we'll be doing it with Morse code. Because then we can use like a piezo buzzer and a microphone in order to like send packets versus like needing to use like radio or something, right? Because like building a radio or like an actual Wi-Fi adapter might be a little bit hard, but we can still effectively send data through 2 devices. So, we'll need to interface with this Pi at some point. So it's still here. Haven't forgotten about it. Yeah, it's Morse code. Yeah, don't you worry. We're using. Yeah, we're gonna have a custom. I was actually thinking, it's kind of brief tangent. I was brainstorming about this. We could have our own. So with Morse code, right? If you look at the encodings, a 1 and a 2 are very different. Look how thick the encoding is. So a 1 is like a beep and then 4 long double beeps, and then a 2 is 2 short, 3 long. I'm like, that's because we're encoding all these different symbols. Where if we're gonna do Morse code, it's gonna be even simpler. We're gonna have 2 pitches. So a 0 is like a low pitch, and a 1 is a high pitch. That's it. So that's gonna let us send data much more rapidly than using Morse code. It's a better encryption but basically, yeah, the data transfer is all going to be 0s and 1s, which is all we need right now because it's packets. So little hack to make encoding better for our use case. I think this is good now. I'm just gonna fiddle around until the code stops breaking. Is this good? Is it mad at me? Oh, something's wrong. Yes, this receive. Oh yeah. Sick. So hella race conditions because they're not actually contingent on each other because it's fake. Right. That's again. We'll go down and mock this more. But at least now we've got the core stuff. So I'm gonna use the restroom quick. This is like my first time now actually figuring out how to pause a stream. Can I even do that? I think there's like a be right back button. Let me see. Yeah, it works. I don't know. I don't think you pause streams. People in the chat are asking for Eric.
Eric is here.
Yeah, let's go on chatting. Here he is.
Fear not, Eric is here.
I don't know who Flightless Ferret is, but so.
Are you satisfied, Flightless Ferret?
Yeah, we deliver here on the stream.
It's on-demand Eric. 15-minute delivery, Eric.
Okay, I'll use the restroom now. I think it's right back, right? My monitor just disconnected and that freaked out. It's like, what's going on? Be right back. Okay. Cool, I'm back. See if it still works. Cool. Nice.
Did you know that Apple keyboard and mouses fit perfectly into your ass pockets? This is great for transport.
Is that just because you have massive? Do you just have massive ass pockets,
Yeah,
or
you
is
just
that?
gotta be thick.
Yeah, I was like. I love that anyone who's like watching the stream is just like, it's like be right back, and then come back and it's Eric's ass. Also, I've got my bottle of sangria, non-alcoholic. Don't worry, we're not aiming for Balmer's Peak in this stream, but otherwise my the stream would be degrading really fast. Sweet. Okay, I think this is good. I'm trying to get these interfaces right, but I think we're pretty clean now. And the next thing that matters here is just like getting, like, I'm trying to go as narrow as possible into the implementing like one function, like open, because I know the moment we delve in deeper, it's gonna get like really more brain power needed. Let me see. Have some sangria, firstly. Yesterday was a birthday party, so I was up way too late. That's why the stream started later. So I literally rolled out of bed. I was like, all right, time to stream. Nice. It's good stuff. Packet, receive. Nice. I think this is pretty good. What do we want to do first? I mean, we want to make this literal code work. I don't actually want to change the high level code now. I think if I did, I'd be butchering the abstractions that we set out to make. So we should probably drill into listen and open. I think that's it. This is where the three-way handshake is. This is the receiver side. This is the sender. What we'll do is, so open is going to be doing, let's go a layer deeper now. Let's just commit to, this is our last high level connection. This is our last friendly interface. Now we're going to be getting into like the obscure territory. So in here, we're going to be doing a SYN. We're going to be wait for SYN ACK. I believe that's how it works. And then send ACK. Yeah, that's my understanding of the three-way handshake on the connection side. Let's double check our friendly military document. Okay, so there's like a SYN sent, receive SYN, send ACK. There's a bunch of states in here. And I imagine some of these states are needed for more complex stuff like multiplexing and like keeping track of basically different connections and ordering and stuff. But if we're doing a really simple thing, we probably just need actually, no, we do. Let's use the official naming. Then I can see why. So basically, after we send the synchronize request, we're in the let me see, active open, create SYN. Yeah. Let's use their actual terms. Thanks, Flightless Ferret. Hope you have a good rest of your day. The stream will be uploaded on, well, Twitch, and I still have a backlog of streams to put on YouTube, so I'll be doing that as well. And I'm also starting I think it's like a newsletter where I'll share random stuff I'm writing to kind of tie in things, so it's not, so there's kind of like a thread of lore that one can follow, but. SYN set active open. Trying to open connection with self-host. Oh, so these are, okay, so these are states, and then triggers. Maybe I should define a state machine for those. I kind of glossed over it. Again, I apologize. The stream's like, one side of it is super high level, like how do we make the internet? It's super friendly. And then the other side is like, hey, if you didn't take operating systems, get wrecked. And it's just like, I'm not explaining stuff, so I apologize. State machine is like, states are closed, listen, sent, whatever. A state machine is just a diagram that shows how you transition between well-defined snapshots of your program. So like, I mean, it's probably obvious now looking at this diagram, but I mean, state machine's still a concept that folks usually have to wrap their head around. I've built many state machines, so I'm probably glossing over this more than I ought to. But for context, at the beginning, we have this closed state. So we can define that in our program. We have closed, we have SYN sent, and then we're gonna wait for a SYN ACK, and then we send an ACK command, and we're done. And so there's like 6 or 7 states looking at here of how we're doing it. We're focusing on the top half of the diagram. So we have closed. I actually don't understand what listen is. Oh, I guess this is for technically speaking, we're gonna have a listen state because both the client and the server can listen because it's a bidirectional communication. We're kind of hacking around it. We're gonna have closed and SYN sent and established on the client, and then we're gonna have closed, listen, SYN received, established on the server. So we're having a one direction communication, but it's trivial to implement bidirectional. So that's why we're doing that. So what states do we have? We have closed, closed, SYN listened, SYN received, SYN sent, established. Closed, SYN sent, SYN received, listening, established. Established. We're gonna keep those just for now. Delete some notes. So when we create a new connection, it's gonna be closed by default. Clean. When we call open, what are we gonna do here? So send SYN request, and then we're gonna do self.state equals SYN sent, and then we're gonna do, and I guess once we're in the SYN sent state, we're actually just waiting. So this is pretty easy. The client sends a request, so it sends a packet. It says SYN sent. Then it's gonna just chill until it receives a SYN ACK. Then it's gonna send an ACK. So we have basically a wait. Now this gets fun. How do we wait? So like, dot SYN response. So while we didn't get the response, we're just gonna chill. This is actually super interesting now because, so technically we're waiting for a SYN ACK, like to get sent from the server. And we're like, yeah, look at it, it even knows. So the comment, it knows exactly what I'm trying to do next. Check local file system for SYN ACK payload. My phone is auto-connecting to my Bluetooth. Let me shut it off entirely. No. Cool. Check file for SYN ACK payload. So we're gonna check the local file system for a SYN ACK payload. And we'll have like basically an interface. Now like there's a lower level file reader we're gonna define. So let's define it up here as a class. I mean, we can keep it simple. We don't actually need a class yet. It's kind of ugly. Like, let's think like how well we want to engineer this. I'm gonna make it a class because, you know, I believe in good defined things, well-defined interfaces. Reader file socket. So what's the design of this gonna be? I mean, we can keep it simple. How about we avoid defining a class until we actually know what the interface needs to look like? Because the hard part is like, you don't want to define an abstraction before you've understood the terrain. Like, you don't want to build a map before the terrain, or else your abstraction will not capture reality well. And it's just like, a bad abstraction is probably worse than no abstraction, because a bad abstraction will lead you astray. No abstraction at least gives you the chance to see how things are working. So we're gonna check local file system. We're just gonna make it a helper routine right now. And we'll note that we're gonna move these out into its own helper library at some point. And And another thing we need to ask here is how we're doing what is it? Like how we're actually checking for a file, like where is this file going to be stored and stuff like that. We can look at how file sockets are handled. I imagine they're just like a file on the computer. There we go, it's in proc. So for context, if you go into the process folder /proc, you'll see a list of all running processes. We can get a bit more detail about them. Some of them are created days ago, some aren't. And then there's a section where they're process based. So each process has its own proc. I think that means what we want to do is when we initialize this Python program, we're creating sub-processes, right? Each sub-process is going to have its own ID. And so what we're going to do is create in proc, we're going to have ID, and then we'll have file descriptors stored in there. So it'll be like, for now, we'll just like hard code it. We don't have to have like a very detailed scheme, but that's where they'll be stored. And that'll mean every time we restart the program, we're going to create a new file, like a proc directory. Maybe just to make sure I don't brick my OS, because like the proc folder is very sacred. It's where like it's being cleaned up when processes are done. Since I'm going to be doing really jank stuff, like not cleaning up, I want to make sure I don't like write a process ID 200, not clean up that process, and then suddenly I create a new process with that ID and it can't write or something. I just like break the machine, which is surprisingly easy to do on Linux, like Ubuntu. We're starting to get into like the RM RF category, where it's like a couple dumb commands can like break file writing. So what we're gonna do is put it in. We're gonna put in dev/proc, which I don't think is being used. Yep. We're gonna make a dev proc. Sudo dev proc. Cool. So /dev/proc is where our file will be. Cool beans. So this needs to be a bit string. Self. And then what we're going to do as well, and we need a way to say if the payload was actually returned. Let's just return none if not found. There's going to be something, okay, I'm kind of a couple steps ahead in my mind here, so let me try and catch up with my thoughts verbally. There's probably going to be a data written here from previous connections, and so rather than having to wipe the synac like file that's been written on the machine, I want to first check and make sure it actually has the packet we want. Like, for example, in the notes they define they have a really clear definition of the send receive, that there's supposed to be like a status bit that is set. And so I don't fully know how it's defined, but now we need to start thinking about the actual payload. And like, basically we have to sanity check that not only are we receiving a packet, but it's the one we want. Maybe we can abstract it away just to be simple right now. Like keep it bare minimum of how much work we're doing. But like, I would say to implement TCP IP, this has to be done. Like, so let's just look at basically let's look in this send area and listen. So the sequence number seems to be the first thing we need to care about. So sin sent, there's a sequence number, established sequence 300. Yeah, this sequence number thing matters. TCP A begins by sending a SYN segment, indicating it will use sequence numbers starting with sequence number 100. Basically, we gotta understand this to build a handshake. Because the whole point of a handshake is to have like an ID specified from the client that is like agreed upon with the server. If we don't have that, that's just dumb. But we know at like a high level we're doing a file descriptor read, or a file read. We're storing like data as files. Cool. Check for synac. I think the area where I'm now not understanding enough is just the core handshake, like what bits are set. So we need to grok this. Yep. Sequence numbers. Every octet. All the data sent over TCP has a sequence number. Since every octet is sequenced, they can all be acknowledged. Okay, I don't know what that means. Okay, so it's just confirming what's been received, what hasn't been. And it lets you do duplicate detection. Got it. So basically you're sending an initial payload saying like, yo, I'm about to send you data. And then the first packet is indicating like how much is coming and the sequence number. And then on the receiving side, it's gonna be like, yo, that's good. And it's gonna make sure that it receives all the sequence IDs up to the number that it is expecting. Yeah, so you can send up to 2 to the 32 minus 1. Yeah, again, like you're not going to send that many chunks of data. That'd be absurd, right? But there's in theory a limit, and if you hit this 2 to the 32, I guess packets they're called, if you had to send that much, you would just split it into 2 different requests, right? The typical kind of sequence number comparisons with determine that the acknowledgement refers to some sequence number. Okay, so we got this acknowledgement. It's getting complicated. Let's find a higher level description of it. How TCP sequence numbers. Packet life. Of course, there's a log for this. Nerd. Nice. This is a bit more friendly. Like, this website at least looks like it's from the 90s versus we were reading docs from the 80s. I guess 2010. It's pretty good. Still looks old. So one thing I think that's good to note here is that packets are just agnostic. So there should be basically a packet listener area on our machine. Just kind of dumb, I know. But like, there's gonna be a packet listener, and then we scan the packet and read what the content is. And we're gonna do one packet at a time. It's like written to our machine. We read it, we're like, new packet. Or maybe there's gonna be like a file, like a folder with a list of new packets that have been written onto the machine. I just need to understand what sequence numbers are better though. So let's just, this article is cool because they're actually exploring like really how it's working. Like they're using a tool called Wireshark, which lets you monitor network traffic. This is actually cool. I should have explored this at the beginning. So they're saying they're sending a request, and then there's all these like, all this stuff happening. There's a bit that is 0 for a bunch of flags, and then it's set to 1. Got it. So the handshake here is done with 3 requests. So there's the SYN, there's a SYN-ACK, and then an ACK. That's already what we know. Very familiar stuff now. So sequence number keeps track of how much data has been sent. It's included in each transmitted packet. Nice. So, okay. So we've got one piece of info. Sequence number, when you create a TCP connection, sequence number is some random thing. Does it change? Ooh, this is super cool. I like Wireshark. I feel like we could really like. This is kind of neat. I mean, it's like not surprising, but it also is when you're like, hey, this thing that we're building is actually how it works, and that's the whole point. But it's still cool when you realize it. You're like, if you open up Wireshark or some of these like networking tools, it's exactly what we're implementing. I don't know. Maybe that's super obvious to people watching, but that still is cool as heck to me. Yeah, so each row is a TCP packet. The time it's sent, super fast. You can see the sequence numbers here. This is cool. Is it increasing monotonically? No, it's not. server responds to the client with a sequence number of 0. Yeah, and then an acknowledgement number of 1, set to 1 to indicate the receipt of the client's SYN flag. Okay, so there's a very clear, like, I'm expecting this from you. Has been increased by 1, although no payload data has been sent by the client. Increased by 1. This is because the present of the SYN or FIN flag. Cool. So this handshake part seems to be like sequences 0 and 1s. Okay, there's some very specific rules they're following here. It's because the presence of the SYN or FIN flag. Okay, this is cool. So basically, the sequence number, the last packet sent. So acknowledgement is how much data it's received from the server, and the sequence number is how much data it's sent. So that's pretty clean. That's basically what sequence and got it. So like all we're doing here is keeping track of how much data has been sent and received in the handshake. That's good. Yeah. So there's sequence and acknowledgement. So now if we read this top down a bit more, we can say, okay, we send the 0th sequence. We have a request, it's ID 0. Acknowledgement is like 1, just default. And then it changes to 1. So these 0s and 1s are very default, like they're indicating the handshake, basically. 0s and 1s are what we care about. I imagine the DARPA document will talk about that too. And then once we start sending payloads, they start going up, indicating like, hey, I've sent this much and I've received this much back. So this example here looks like a download because the response is significantly larger than the request. Like it's like they're asking for an image or something. Which is probably typical. You hit a server and you say like, yo, here's a GET request. So you're sending an HTTP call, but then the server is sending you back like a massive picture. Okay, I am a writer, so let me do that. Let's clean up these notes a little bit. A relative sequence number of 0. I guess that just means the number relative to the previous sequence number is 0. Like it's like 1 higher or something. We're gonna assume a fresh connection. Again, we're doing like bare minimum, so we're gonna start our sequence numbers or relative number at 0. That'll be our base. If we're sending multiple connections, we'll probably have different sequence numbers, right? I imagine. Because it sounds like sequence number is the way to identify a TCP packet. They must have it detailed here. propeller rules. Yeah, we're gonna have to, obviously for sake of time, we can't follow every single protocol rule. But I rather get the core ones right. So what do we need to send bare minimum amount of data? We do need sequence numbers. We do need a handshake on how much data to expect. That makes sense. Acknowledgement number is 0. So sequence number, so in the first packet, sequence is 0, acknowledgement is 0. So that's just a default. Cool. Server responds, so this is syn ack. Yeah. Yeah. Now it's starting to make sense. Cool. So packet server client. So this is packet 2. Server sequence equals 0 and acknowledgement number 1. So this okay, so basically we're just putting this into the syn ack three-way handshake and like simplifying like each one. Like the handshake hasn't changed. It's still syn ack, except there's like these sequence bits that need to be set to follow the protocol, which makes sense. Because again, the whole reason is like, how am I supposed to read a packet and know what it's talking about if there's not like a very clear sequence acknowledgement number? Like I have no clue if it's the first packet in a sequence, if it's the second, is it part of a previous sequence? By having the sequence number set, we're gonna be able to read the file system, pick up the latest packet, and we'll know if this is corresponding to the first packet of our new sequence, or if this is like a payload packet from the previous sequence. Because we're just gonna have a file loaded with like payloads that have been written, and we're not gonna know what any of them mean. And I'm doing that so that it's that's just how TCP is implemented. We can't hard code semantics into the file system. Like we can't have a labeled file that says first call, second call, because that's not fair. Like that's not how this is built. And like it's fine to make simplifying assumptions, but we don't want to violate the protocol, or else it's not fair. Yeah, incremented the 1. It sent 1 bit of data, so it sends a 1. Yeah, that makes sense. They both sent a bit of data to each other, like a bit of relevant information. The client syn, which is a 1 bit, and then the server sent a syn ack. Sequence numbers. Yeah. So this is ack. So we're gonna go client, server, packet 3, packet 3, 1, ack number of 1. Okay, this is actually like really simple. Like it felt complicated when you don't know what it means, and then it like I can explain this now. Number of 1. Okay, so basically, sequence number is how much data we've sent. Acknowledge data response. At the beginning, this neither of us have sent any data. So when we're sending so there's 3 calls, right? Again, we can just say like SYN packet. This is the SYN ACK response packet. And then the third is the ACK packet. So we have these 3 packets we're sending, right? SYN, ACK, ACK to do the 3-way handshake. And on the first packet, nothing's been sent, nothing's received. So these are 0. Then the server responds with 0, 1 because the server has sent 0 data up to this point, but it's now responding. So let me yet. And then the client is sending an acknowledgement to the server saying, hey, I've received 1 piece of data and I've now sent a piece of data. So basically like when you receive a packet, it says sequence and ACK, it's saying how many bytes of data have you sent and how much have you received? So 0, 0, 0, 1 means, again, the server has sent nothing, but it's acknowledging that it's received something. And now I've already sent data. So like if you get this sequence number of 1, it means you better have received a sequence number of 0, otherwise some shit's messed up. Like you haven't received all my data. And then acknowledgement of 1 means, hey, I also got a packet of data from you. So like we're chill. And then once you get into the payload, then it just starts being like, how much are you sending, how much are you receiving? And it increments proportionally to the number of bytes you're sending. So you can calculate that in some way. But those numbers are basically going to increase. So, and this is how it sounds like, I mean, it's in the name, sequence. This is how we make sure that we're reading data in the right sequence. If we have a list of packets, we should be basically reading sequence number in order and acknowledgement number, I guess, in order. I don't fully understand here if that's the case, but like, it sounds like these are being used to make sure that we're able to send data at different order, but then we read it in the correct order, which is good. It's a good thing. And that's actually realistic, even on, even if I'm implementing this in Python, just like locally right now, this will be how it works because, I mean, there's a chance my server delays for a bit and the client is faster than the server, and like the server needs to read the file. And the file system would be like, what do I need to read now? So that's pretty cool. So check for SYN-ACK is really just looking for packet with SYN equals 0, ACK equals 1. Yeah. Yeah, SYN is 0, ACK is 1. And then what else do we got? So check for SYN-ACK. This is kind of a nice little, I guess we're getting a weird layer of abstraction in between file writing and like SYN-ACK stuff, but we'll keep it for now. Did we find the packet? So we're looking for a packet on the file system. We're only returning 1 if that packet exists. It's cool stuff. Now what? Closed. Let's delete this. Where does the SYN get sent? Like, how do I send? Yeah, like we haven't done this part. I'm gonna rename these to have packet at the end because there's some sort of interface we're gonna end up having with packets, the file system. And like, I don't know what it's gonna be called yet, but I'm just seeing it emerge very quick as I write this. Ooh, look at that. this word is wrong. It should be sequence. So the sequence bit should be, so in our initial SYN, again, I'm trying to remember it just from first principles here. 0, 0. We've received nothing, we've sent nothing. ACK equals 0. That's all we need. Sequence bit equals 1, ACK bit equals 1. Oh, we're gonna have a weird, it's gonna be funky. It's gonna be funky. And I can explain why. So, it's fun. We get streaming while getting in the weeds is I'm noticing very tricky because I forget to talk. I forget to, so I actually have to communicate in English, but then I'm like so in the weeds, I'm like thinking in terms of like zeros and ones. So basically we're gonna end up having a, let me just write it out. It'll make sense. Dev, okay, let's say we have this, we already said our process, like our packets are gonna be stored in dev proc, the corresponding process ID. Let's say we have proc 0. So process ID 0, let's just say that in terms of, actually let's make it really specific. 1, 2, 3, 4, 5. Permission denied, come on. Sudo. So our default process ID is going to be 1, 2, 3, 4, 5. That's how we identify that this is the hard-coded TCP implementation. And within there, we're going to have dev proc 1, 2, 3, 4, 5 in. Is that defined correctly? Ooh, this is weird. What's going on? Sudo and out. Let me just load it up quick. Okay, we have a directory, and it has an in and out file. The in file is going to have packets that are sent from the other computer, and the out file is going to have packets being sent from this computer. And you might be asking, well, I'm asking, is this part of how the protocol is done? But I read in the document that basically this low-level abstraction can be implemented however you want. Like, they don't give a crap about how you store files. TCP is all about the packet specification with sequence ACK to have a mathematically correct handshake policy to ensure that you send packets in the right order for a connection. I could store these on cardboard if I want. I could store these files any way I want. I could print them out, I could do whatever I want. I could send data however I want. There's no guarantees on the speed. The only guarantee is that packets arrive in order, and that if packets are missed, the server knows, because there's like a very guaranteed way, and there's like following rules about the packet format. Anyway, so basically what I'm saying here is this was a design decision by me, that we're gonna have an in and out folder, and we're gonna end up writing a library, I guess, that scans in and out. Like our driver will scan the input folder or out. Our driver will scan the output folder and put these on a Raspberry Pi, all these packets, and our input will scan the input folder from packets that were written by the Raspberry Pi, which technically we're not gonna, it's gonna be weird right now, because like, we need to send and receive data, so we need a microphone and a speaker on both devices. It's gonna be funky. Getting the hardware part's gonna be wild, just because like, let me just write this down as like an unknown. Speaker. So we need a speaker, and we need I don't even know if I need 2 Raspberry Pis. I might be able to do this with a laptop and a Pi. Could technically do it with 2 of any computers. Like the Pi is just like fun because it's like a little board, lets me write closer. Technically speaking though, like this could be two laptops just beeping at each other. But I think the Pi gives me a nice low-level interface for being able to like read bits, like that it's listening to and stuff, and I appreciate that. Whereas like with a speaker, if I plug it into a laptop, I need to be reading through like USB-C, compat and stuff, and it's just kind of weird. But both of them need to read and write data. That's gonna be weird. I don't know how to spell interference. Basically, the thing I'm realizing is like, we're not there yet. We're not doing it in the stream. We'll get to it. But in the hardware level, I'm like, yo, there's going to be packet interference because like, let me just Google it quick. How to avoid Morse code interference? This must be a thing. So waves are about frequency. That's basically, that's the way this shit works. So, I don't know enough about signal theory, but I imagine we can like denoise waves to be like, if you hear, if a wave comes in with two different sounds, we can probably extract the two different pitches that contributed to that wave. I don't know how to spell this. Fourier Transforms? I'm pretty sure these are called Fourier Transforms. Decompose function based on space or time into functions depending on frequency. So, calculus, we're back, yeah. Thought like with calculus. So I don't know if this is exactly what we want. This is transformation functions depending on space or time to function spatial frequency. Basically, if wave frequencies, I need multiple waves. If they're beeping at the same time, that's going to be confusing because I need to know like which sound is input and output. The thing sending, must have a different frequency than the receiving computer. I probably like, I don't know. There's gonna be a whole thing about like answering this question. This sounds like a rabbit hole and a half. We can hack around it because I don't have to claim I'm like a signal engineer, but like trying to figure out how to denoise waves. Build up here. That's basically where we're at. So I'm just like, because we're building an adapter that's sending. We're just gonna use sound waves, not radio. We have to figure. Yeah, stuff's good. Nice to see you in the stream. Yeah, this is gonna be a stream. Fourier Transforms is gonna be a whole stream, I imagine. if we have to actually grok this. But yeah, this is good. This is good looking stuff though. I like this. But you know, we're software, so let's go back into the safe haven of software engineering. Yo, what's up, Connor? Wow, we got a cool squad in here. Where are you guys joining in from? Are you both in Sweden right now? Are you in England? Are you in Ireland? LA. Damn. Not what I expected. Pittsburgh. Okay, cool. I'm in Mexico right now, but it'd be cool to meet up sometime. I'd love to. Also, it's great to see you in the stream. I really love how folks show up with just like pseudonyms, and like I don't know who anyone is, and then like a day later somebody will text me being like, yeah, your stream was cool, and I was like, who were you? Were you like Fat Sausage 29 or something? And it's just like, it's really funny. I'm in Mexico City. Okay, in UK, that makes sense. That checks out. Yeah, I'm in Ciudad. That's good stuff. But yeah, for context, if you guys weren't in the previous, Don Jolan. If you guys weren't in the previous stream, we designed, well, we were asking the question like, what's the internet? We're trying to build it from scratch. The requirement is to follow the original TCP IP specification. So like we gotta follow the rules that the military put out. Where are they even? Yeah, here. So we got this like OG document from 1981. There it is, DARPA Internet Program, and we're like, and I've got a Pi, and we're gonna send data to probably another Raspberry Pi or something. We're just basically drilling down through. It's actually getting really fun, depending on your definition of fun. I think this is cool as heck. We're defining these like lower level abstractions. So we've got our server for like sockets. We're using like Python processes just to like, you know, not reinvent every wheel. We're reinventing one wheel, which is the internet, the unicycle of the internet. So we go down here, we have connection. We've got some like logic here for handling open. We're working on this one function right now to do the TCP handshake. And to do a handshake, and we're going down another layer. To do a handshake, we got to do this thing called like SYN-ACK, or SYN-ACK, which is just basically sending packets that like agree on like stuff. It just means mathematically we're sending packets in the right way. Yeah, it is turning out to be mad. The fun part is I've never done this and I don't know where it's heading. So when I started this on a live stream, I was like, yo, this might just you gotta scope aggressive. But now the thing is I'm using file sockets. So what that means is in my file system, I've created a directory called dev proc. So for refile proc, all your processes are defined in your file system. So you can actually look at any individual process. I think not many people actually realize this on Unix. You can like open up an individual process and see all the file outputs, memory, mounts, like packet input output. And to brick our machine, we're gonna make a dev one. So dev proc. We have a process 1, 2, 3, 4, 5, and we're gonna be writing packets and then writing a driver that puts them onto the Raspberry Pi, beeps them in Morse code. That's where we're about 10 hours in. And yeah, and then I got into the math part. I should actually ask you guys a couple questions. You're both here. For context, and anyone else who's like, yo, who are these randos in the chat? They're cool dudes that do robot math nerd stuff. So actually, is anyone in the chat? I don't know who else, just people are sharing computers. Do y'all know how to denoise waves? So like, we're gonna have Morse code. We're gonna have this Pi. It's gonna be beeping 2 pitches. One pitch will be so technically we're not using Morse code. We're using a Morse code. High pitch is a 1, low pitch is a 0. And we're gonna have 2 different devices, both beeping. But I'm like, trying to answer this. How do we send and receive beeps without the sounds interfering with each other? And I'm like, that's like wave interference, right? Like two different pitches are going to be sent at roughly the same time and are going to cause weirdness. And on the receiving end, I need to hear this like middle pitch. Maybe it's like a combination of 2 pitches. And I need to be able to extract the signal from it reliably. The alternative is I just have like sleep timers on both machines so that they never send and receive at the same time. But like that might be the functional solution, but it's just kind of annoying because like I know that this is a solved problem. So if anything comes to your mind, if Fourier transforms are the way to go, that'd be dope. I don't actually know if that's the right way though. So, but for now, I'll just jump back into implementation. My goal here in this stream, and I'll see when my brain starts getting tired. It's kind of random, but like I'm trying to get as much of these low-level interfaces done so that in the next stream it's just all hardware. Yeah, so that's what's up. and I'll jump back in here. But nice to see you guys in the stream. We got to catch up outside of here, just to be clear. Cool. So send SYN packet. We're gonna write to the file system here. We'll have a separate none, or if the packet is found, we will return just literally the bit string. I guess a TCP header is supposed to be a certain length, like 64 bytes or something. We'll figure it out. Eventually this payload, right now it's a string. That's abomination. It should actually be a struct. Thank you from the chat. Do we have the chat bubble showing up on the? Oh, we don't now, so that's good. Miss you guys. Let me see. Check for SYNAC. I think that's the main thing. So we get a payload. So we've sent the SYN packet. We check for SYNAC. Once we got it, we're gonna send an ACK packet. Let's call it got SYNAC. Yeah. SYNAC. And then we're gonna do self dot send ACK packet. Thanks, Gabe. We will have fun. Send ACK packet. Cool. Let's do some boilerplate. This is going to be the same as send SYNAC. So basically, these two functions are going to end up being identical. They're both just sending a packet. Right? Again, keeping it abstracted away right now, because I want this is all about abstractions, right? If you write a lot of software, you'll notice it's super important. We have this open function. I don't want to be dealing with file writes in here. That's confusing as shit because it's really hard to test. Basically, if you have a function that's like more than 40 lines, you're doing something weird. To prevent it from being like really long and having a bunch of different stuff going on, we're using higher level functions. And then each of these are going to use file writing. So we're separating the notion of dealing with the file system into its own abstraction layer. But it seems to work right now. So let's just keep it real. So send SYNAC, or send ACK. So this is going to be sequence is 1, ACK is 1, right? If I double check my notes, I'm pretty sure there should be a 1-1 packet. We're sending. I mean, this effectively opens the connection. Like that's the handshake. It doesn't look that crazy once you write it out, eh? Let's look back at our friendly diagram. Where is this? It's like buried deep. This is mask of ASCII chart. It shouldn't be that hard to find. There it is. So we're still in this top half. Let's so active, closed. Send sync sent. So that's gonna happen. We got 2 levels of state. SYN sent. We got that. Now what's the next state? Next state is established. So we receive the SYNAC, we send ACK, and we just set our state to established. So it's gonna be right here. Established. One thing I don't like is that I'm using strings here. Does Python have enums? Bobby. Come on, Bobby. There. Oh, Python does have enums. Sick, dude. Sick. Yeah. This is dope. Everything is a class in Python, it seems. What a class is. Yeah, basically what I'm doing here is like defining a state struct, just because like doing a state machine using strings, naughty. Because if you type something wrong, you will destroy your state machine. You will not know why. It's super annoying to debug. And all you need is like one letter wrong. And you've already seen, if you're watching the stream, I spell words wrong all the time. Oh, now the other thing I'm looking for is how to define so I guess each enum needs to have a number. That makes sense. That's the same as in C, in enumerate, or C++ in enumerated type. Each field has an integer corresponding to it. Defining an enum. Now we're trying to define a private member, which is an enum. A flag in a class. Yeah, that's what we want. Is this like how you do this? Is this garbage? Ugh, yikes. Like, ew. That looks nicer. Do we have to put it outside though? Like, I don't, scoping, come on. I don't, the state, like the state is a private member of this class. Ironically, I feel like my internet's getting slower the more I do streams. I know that's an enum. They literally didn't answer my question. Some SEO garbage. I guess. You know what? YOLO. Doesn't seem like anyone's giving guidance. We're just gonna go unhinged here. Internet is lagging. Okay, state. We're gonna define it. I think listening is okay. Listening. I'm chill with that. We'll keep that. Did I open something dumb? Can I make this stop? I bet you it's Geek for Geek. Look at this web page. It's just infinitely loading ads. Like, come on, guys, stop. Look, it's like freezing my whole browser. What trash? Do I have any more of their website open? I can just close all their tabs. Yeah, my internet's better. What a garbage website. I mean, it's got good information, but like, yikes. Come on, guys, it's 2022. Your webpage shouldn't crash my browser. Syncent? Yeah, this is nice. Anyway, point of this now is we can do closed. We can do this. So we're not using strings anymore. They're defined here as ints. They're explicit. If you get the type wrong, it'll cause problems. Yeah, that's nice. Just basically, strings are naughty. If you remember that, you'll have a good takeaway as a dev. State.syn. Syncent. Sounds like a Chinese tech company. Syncent. Maybe like Singapore. Nice. Okay, that's cool. Now what? I mean, this is the open function. Like that's roughly what we want. Now what else? We need listen. Cause yeah, so we're gonna have the first calls that are made are listen and open. So open and listen are gonna work hand in hand. They're both implementing the handshake. So listen, what is listen doing? Listen is waiting for a SYN command. So it's doing the exact same thing. Like we could literally just hijack some code here. This is probably gonna become a function. Where is listening triggered? Passive open. So there is a thing here that we need to be aware of. I'm just gonna say we're default in the closed state, and then if you call the listen function, we'll put you in the listen state. It's kind of different than the state machine here, but like, I don't want to implement a passive open. It seems confusing. I want to be explicit that like we're now listening. Here, there's the state. I guess we don't have a closed state. Oh, we do. Yeah, we should. There it is. Yeah. So listening, got SYN, well, not got SYN. We need a timer in here because that's having a while loop with no sleep. Oof. Let's put a 1. 1 second sleep, it's chill. Check for SYN packet. It's gonna almost be identical to this function, SYN. So a SYN packet will be received on the server. How's that gonna look? So 0, 0. We're looking for a 0, 0 packet on the server. And actually, or this is kind of just like not necessary, but like, yeah, we don't have to order the function. It just annoys me that they're sorted by synac first, whereas SYN is actually the first function, and we're gonna move it. I can't deal with this. There, better. We actually got to move this one too. Synac happens strictly after send to SYN. I want them to be in order. That's better. Oh, good. Wow, we're actually getting some stuff now. We're writing code, guys and girls, and non-identifying. We are doing cool things. Check for SYN. If the payload's there, get SYN is true. And then we bail. Oh yeah, we have a
got syn. Yeah. And now the state needs to change here. Syn received. I think that's the name of the state. Yep. Syn received. What happens here though? Like where? Oh, receive ACK. Yeah, because the server is now waiting. So the server waits for a syn command. It's gonna dish out a syn ACK. So right here. Yeah, we're writing the same code many times. I don't like that. I want to hear a good joke. What do you call code written twice? It's called a function. Ha ha ha, get it? Because if you don't write a function and the code's written twice, that's really dumb. I'm surprised the stream's almost at 3 hours. I barely slept last night. I like slept in. Yesterday I just had like literally sangria, which still got the sangria soda, and micheladas, and like a bunch of Mexican food because it's my partner's birthday. But I was up way too late, barely slept. Usually I can't code the next day if it's a long night. But I think this is just a fun project. And I think when stuff's fun, it's much easier to do. Nice. We need a check for ACK packet. Here. And what is an ACK packet? An ACK packet is sequence is 0, ACK is 1. No. Sequence is 1, ACK is 1. Should both be 1. It's the final packet, right? Sanity check. Yeah. Both are 1. Yeah. Yeah. This is like, I don't know how this is gonna look, but like this is silly. I mean, I guess it's okay to have like a packet check that uses a low level utility library, but at that point I could just remove this layer of abstraction and we could have like file calls. I just don't know what that library is gonna look like. I think we're getting there though. First we're gonna mock those though. Syn received, synac packet, waiting for ACK, got ACK. Oh, now we need a state transition. I think this puts us in an established state, right? Yes. I think that's how the diagram works. Estab. Cool. I have no clue what happens here, but like, that's a bunch of chaos. It's a bunch of stuff. I consider success if we can just send data and it's received. So I don't need to send closing requests and stuff. I'm not even doing that yet. I just want, but we just defined the state diagram, all this, we're 50%, arguably more than 50%. Because now that when connection's established, we can just send and receive. Oh, and I guess receive, okay, so how this state seems to work is there's gonna be a bit called fin end, and that'll trigger the closing. we don't really need that. That's pretty trivial to add. To get through those, so here we've got this. Receive. Send and receive. Cool. So send. Send needs to actually break stuff down into packets, like IP packets. Which we do very ad hoc. Send data packet. Yeah, that's how it works. Yeah, so this function is going to be responsible for breaking down the full payload into IP packets with the correct TCP IP headers. I don't quite know where it's going to happen here. I think it'll be this function. Are they called TCP packets or are they IP packets? I don't get it. I need to understand how this is happening. They had this tutorial, where was it? This is nice. So the sequence and ACK headers are still here. So they're sending 725 bytes in this example. So there's a response. How does this work though? So is this, they just drop this being like, yo, it's 725 bytes, but I'm like, how do you send that? So they're calling it TCP packet. I feel like I'm missing something. I guess that is true. Okay, so there's an interesting thing here. So there's HTTP. HTTP, I think that's Hypertext Transfer Protocol. Yeah, Hypertext Transfer Protocol. So HTTP has its own rules, which is like sending and receiving responses, but it's not TCP. We could build HTTP on top of TCP, but I don't care about doing that right now, because that's just like, that's broader scope, right? Like we could build anything on top of TCP, but we don't need to do that. The point is, this tutorial is explaining both at the same time. right? So they're saying, oh, the server has an HTTP response, which is how Wireshark and like how a request would work. The server's actually responding. I think what I'm curious about here is like the acknowledgement number and everything's maintained the same thing. So you can implement HTTP using TCP. You have to keep track of how many bytes have been sent and received in a request. After the response is sent, it's going to close the connection. So we are, I guess, implementing HTTP or part of it. This doesn't answer how to send packets. Like, I get the handshake. Now, how do I send data? Yeah. I got the code defined for us here, nice and. Did we do the send received state? I feel like we skipped that. Oh no, we got it, cool. I was like, did I miss that? That's pretty dumb. Established where? Can I just define, okay, I think we already went down this rabbit hole. This keeps confusing me. That like there isn't a TCP doesn't define the packet size. That confuses the heck out of me. So how do they do it in this payload? They're saying like, they're sending like 700 bytes at a time. So here's the TCP, 000, boom, 725. So in our single request, they sent 725 bytes of data. I'm still dumb here. How many bytes can be sent in a TCP packet? I'm getting the names wrong, so that's okay, 64K. I think this is supposed to be turned into packets, like. Yeah, it's stream based. Yep. Yeah. IP datagram. Yeah, so the TCP segment can be contained in a single packet or reconstructed. Okay. So there's this IPv4, IPv6. Let's use IPv6, it's newer. Because I don't want to use the old one. I say as I implement from scratch. So there's stuff here about segment size basically, and like maximum segment size is equal to the largest IP datagram. minus the IP and TCP. There it is. Is this the IP doc? Ah, okay, cool. Now we got it. Who made this? Man. I'm gonna be so used to reading just raw text documents after this. It's 98. Cisco and Nokia. So is this supposed to be like broken down? Like, is this? I need to see the connection of TCP to IP. That's what's getting wonky here. They don't even define it. The heck? The hell? This looks like the IP packet. It looks similar. PDCL. Maybe this is IPv1. Because there's like wait, is this part of the TCP packet? Okay, no, we got this. TCP header format. Nice. Now what's this? Checksum. Yeah. Maybe Wireshark. Maybe Wireshark explains how to do this. This is literally like UI. I mean, I can see it happening. I'm just trying to fundamentally. I'm trying to see like how to actually implement it though. Cool, yeah, okay. Header, payload, something else. I don't know, I don't care about UDP. You and me both, homie. We're both having trouble explaining this. Okay, so TCP is implemented over IP. I think that makes sense. I think what it's saying is TCP is a handshake, and really everything under the hood is just packets, like a data packets. And so TCP packets contain the payload that does both the handshake and the data for IP. So So you could shard TCP packets into a bunch of IP packets. I think that makes sense. So let me look at an IP packet just quickly. So IP packets are going to have like the data. So this shouldn't make sense then. TCP. The data section is the TCP thing. Oh, I recognize this diagram. We saw this in our first stream. Khan Academy, making everything make sense. Ah, yeah, this is perfect. Look at this diagram. Oh, I love Khan Academy. So everything is IP packets. And since we're doing TCP, the data of the IP packet will be the whole TCP segment, which will be the headers, which is the two parts we care about so far is the sequence and acknowledgement number. And then the data part of TCP, we're going to send a bunch of TCP packets. Yeah. This makes total sense. Hallelujah. Protocols, making things make sense. And that explains how you can build UDP on top of IP, because for a UDP, you would just have IP header and then UDP, or IP data, and the data would be a UDP segment. And I bet you I can Google that. I bet you that's a thing. UDP packet. We're not doing it again, but look at that. They're even using the same thing on Khan Academy. Ha. Ha ha ha. Oh, it's actually so clean. That kind of makes me envious. I'm doing TCP and not UDP. Look at that. Why is it so simple compared to TCP? Like, why has TCP got all this shit? What? The heck? So UDP must be missing stuff. UDP, you can lose stuff. So the answer, should I use UDP or TCP? The answer is going to be, can you lose data? Yeah, speed versus reliability. Oh, that's cool. What do we give a shit about right now? I think we care about reliability because the internet couldn't be built on UDP. Like, right? Like, that doesn't even make sense. Like, what kind of things use UDP? It sounds awful. Oh God, we're back here. Oh, and there's so many other ones too. Transport layer. So I'm going down a rabbit hole. I'm curious. CubeSat. Bunch of nerds. Lake Lighter. Deep space links. Damn. Tsunami UDP. Damn. What's the weirdest one here? Express transport. Oh, they're all corporate. I like this one. Fast and secure. It's owned by IBM. I guess they all use IP. I mean, they don't have to use IP. They can send ones and zeros however they want. But if you don't use IP, it seems kind of dumb. IP is so simple. Oh, so VPNs use UDP. There's a bunch of security stuff. It's a different field. I love how they all put scalable and reliable in the name. It's so marketing. I think my favorite one, like, you know, there's like Facebook memes from like 2012 where it's like, you put a picture and then you label your name. This is like, which networking protocol, which transport layer protocol are you? I think I'm a CubeSat. If I had to pick one. Yeah, I think I'm a CubeSat. This one speaks to me. What is a CubeSat? Interesting. I want to build a CubeSat. So why did they make their own protocol? So it's 32-bit. Got it. We already know what sockets are now. Stuff's making a lot more sense once you build it. Huh, it's kind of cool. Oh, sounds like somebody's at my house trying to buzz me. Someone will get it. Actually.
Close at least, sorry.
Am I being pinged? I think it's just spam. Yeah. So I guess CubeSat, like, people make their own protocols to find out where they get a good hybrid of space, throughput, speed, reliability, probably security. Although I don't fully get why security is a thing. I guess you could probably split packets up in clever ways to have security. Like, you send payloads in a way where if your packets are hijacked, it's harder to like reproduce like the order or something. That's maybe just an idea. I have no clue. I'm gonna write that down actually. Is like, I want to launch a satellite. I think that's cool as shit. That's another topic. So yeah, recap. Whole point of this stream is I'm trying to do stuff that I've been like thinking about but I haven't done. Launching a satellite is really cool. I'd love to do that. So I will do that in a future stream. Once we've built the internet, and once we understand how the protocols work, we can launch satellites. I'll see if people are interested in that as a stream. Anyway, I think we're good now. We're back into the TCP level. We understand now that TCP, so it's all just IP packets under the hood. So all these packets I'm sending, send packet, get, whatever, they should all be TCP packets on the ground level. And we're implementing a TCP transport connection on top of it that's going to read these packets in very particular ways. So we could actually abstract this. We could build UDP on top of this too. We could just say TCP connection. Let's call it TCP because that's what it is. And I gotta rename this now. The reason I'm doing this is because if I open source this library, I want people to be able to build UDP on top of this. Maybe it could be a fun exercise for like a viewer. Would be to like take this and then build your own UDP protocol or build your own protocol. Although building your own protocol sounds super tedious. Because like then you got to think of all the rules. All right, where do we want to go next? We want to check for send, check for act, check for synac. We're doing the send now. We've listened. Yeah, we're doing send and receive. And I think both of these now are going to be just sorting sorting packets by either sequence or acknowledged numbers. That's my guess. So send is going to be, we want to keep this abstraction really simple. Send will take a payload, a bit string payload, and then send will split into IP packets. It's actually TCP packets with correct sequence ACK numbers. So it's TCP packets. We're going to use the correct sequence and acknowledgement numbers to make sure that the server is receiving the payload in order. And then we're going to yeah. I mean, we already know what split is. Split and a payload. And for each one, we're gonna send data packet. Do we implement this? I don't think so. Send data packet. So we'll just do it here. I mean, we already have send packet, so let's just put send data packet. Yeah, there we go. I don't actually know how seek and ack are going to work here because we need to somehow pass in state of the amount of data sent in this request, right? Otherwise, it's going to be weird to sort it correctly. Like we need state management here. Is state management request based? I think so. I think state management is going to be, I think it should actually be up here. Yeah, it's kind of weird because I don't want to put a state variable for ACK and then use it in these functions because I want to hard code ACK in here. Like I want it to be stored in these functions. So there's no way to send a packet with the wrong sequence or ACK bit. But once we get here to send, we need to maintain a connection with a global set of amount of data packets sent. So I think it's probably just going to be an addition. Yeah, okay, I know how to do this. So we're going to say bits. Okay, we're going to know that sequence and acknowledge are derived attributes based on the number of bits we've sent and received. Yeah. And then what we can do is in close listen. we're gonna have to split into TCP packets, and the last one will have padding added to it. And then every time we call send data packet, we can actually send a half TCP packet. So we can send say our payload's like a megabyte, and each of our TCP packets is just over a quarter. One of the packets will overlap, so as in there'll be dead space. So like half the packet will be filled, and there'll be all this empty space. We could use the packet size as a header to like specify how much is sent, so we don't waste. We're not sending dummy data, because technically on the receiving end, we need to read exactly how much data was sent. I was trying to think of a way to work around that, but I think it's needed. I think bits sent should be payload, not. We actually have to check. Just look at the specification. They'll explain this in the doc here. Actually, this article above, I think, explained it better. Packets payload. Sequence number. So I need to figure out if sequence number is data, or does it include a header or not, basically. is what I want to know. Well, we could deduce that sequence doesn't go up by 32 here, it goes up by 1. So I think it corresponds to payload intuitively. The reason being is the header is always a fixed size. So, and the fact that it is 0 and 1 here indicate that they've excluded the TCP header size because it's implied that if you have a hardware device that reads a certain number of packets, like reads packets, it'll read either 32-bit, 64, it'll read whatever size. And then since the TCP packet header is the same size every time, from my understanding, the payload is the part that differs. And so this is to track the payload because it's implied that, oh yeah, any call that comes in will have a header. So let's subtract bits from that, determine the payload size, and acknowledge it. Because if you have a half packet, not the full size of like what we can send in one IP packet, we want to make sure that the data size is the exact number of bytes. So we don't send, if we don't basically send an image and then send an extra 20 bytes after the image. Cool. I mean, that's pretty clear to me. So. Use the restroom again. Use my be right back button. So I'll be right back. Cool, we are back. Okay. I'm just trying to think of like how much of this to implement to get it right the first time. Like how much of send, receive. Because I think now we're getting into like the actual just like Let's see, receive as well. Let's just assume every payload is 1024 bits. Yeah, so we'll assume every data packet is 1024. Let's try to be exact for now, just to be simple. And then we'll do self dot bits sent plus equals. That's pretty simple. We'll extract that part of the payload. Yeah, and sequence will equal the number of bits we've sent already before we increment it at the end. ACK is whatever ACK is. It shouldn't change. Just to double check here on the send, let me open up the thing we were looking at before. Acknowledge at 1. Yeah, so the 1, yeah, okay, that makes sense. We're literally just indicating how much we've sent and received. That's all these bits are. So they should, at the beginning when we do the handshake, they increase by 1s. Just keep it really simple because they're representing we're reading a bit. And then when we set a payload, I assume we're sending the data length minus the header, like the total packet size minus the header. And even if that's wrong, it won't break anything because we're making that assumption on both send and receiver. And now I think we need receive side. Receive is kind of interesting because so send takes a payload, break it down very clearly. Receive needs to somehow build up a payload. So it needs this notion of like, when does the payload end? Like how much data am I going to get? I suppose that's the point of closing a connection. I imagine it's like, we could say that we just keep receiving data. We append it to our global payload until we're done receiving data. So let's keep it simple. Oops, let me see. So and receive is also just gonna like, there needs to be a way to indicate that it's the end, basically. And I imagine this is where the fin bit comes from. Where is it? There it is. Yep. So you can actually see it right here. It's going to receive a fin bit, send an acknowledgement that it's closed. I mean, we can also simplify the close. We could be clever, because I know there's like some like handshake and like stuff you got to do to close. We could just say like, when you receive the fin bit, just shut off. just be like, we're done. But I see what this is all for. The reason we probably have all these states is because just because you receive the fin bit in one packet doesn't mean you want to shut down, because you might still be waiting for like intermediate data. So we actually have to do a check to verify that we've gotten all the packets in our stream, which is true. That is true. I'm trying to think of the easiest way to work around that without having to write all the states, because it's just like we know what it's doing. I see there's a time wait. It all makes sense. Like these are just handling the edge case where we don't receive the bits. Let's optimize for the happy path first. Check, we got all the we're just going to throw an error if the data's not there. So yeah, I see here, this is actually really important. We're dealing with packet ordering here. So I do think we actually have to get this right. As an interface, like I don't think we can skip around that. This is like very clearly part of the protocol. If we don't, I think it'll bite us later because we essentially need to make sure that packets are sent and received in the correct order and we get them all. That's the whole point of TCP. Like if we want to simplify, we can just do UDP where we don't check all this. But that's why UDP isn't used for everything. Yep. Let's close. So what is the, let's go back to this article. Yeah, so you send the fin flag. Yep, sets the fin flag. Sequence number. Yeah, I guess that's important because we can like we can free the port or whatever we're trying to do. So it's cool. It actually doesn't specify. We don't specify the expected length when like. So we could make a new protocol where we in the first packet specify the length. But I guess the reason TCP doesn't do that is because if the first packet comes in second, like if they're all out of order, TCP still works because all it does is it's like handshake, send data. Doesn't matter. Just send it, and then eventually send a finished packet. And there's going to be weirdness in this end part because basically if the finished packet receive fin, yeah, close wait. That's the yeah. Here we go. Yeah. So I guess with sockets, when you implement the bind function, that's just reserving the socket, like it's reserving the port and everything. And then you could do tons of TCP sessions. You could probably open, close, And then unbind is like a separate thing where you release the resources, even if the TCP is closed, because it's just packets being sent to an address. Cool. So I'm going to do a simplification on the fin bit just for time. And because the requirement I set back in day one of this is I want to be able to send a valid call. My requirement isn't to handle every edge case. So like I'm not aiming for a robust protocol at the moment. I think that's novel. I think that's good engineering, but the objective here broadly is learning. So going down every single technical to learn these streams of following a few rules. So what we're gonna do is, I just want to make sure I wasn't like missing something. Basically, yeah, we get a fin bit. We're still gonna do a send, like a confirmation that we're closing. We're gonna do a final pass for packets that we haven't processed. And we're gonna make sure we have all the data. If we don't, like if we get the fin bit and we're like, yo, we haven't received everything, we don't have to do a final pass. That's extra. Like, we could say like at minimum, we're just like, yo, if we get the fin bit, we haven't received everything else, freak out. Bonus is scan packets. So if we do actually have all the data, we just haven't scanned for it, like it's on the machine, it's been received, we just haven't processed it, rebuilt it up. We can do that now. So we'll do that. And then we will still do a send close request. Like we're gonna follow the closing protocol. We're just skipping a couple parts of it. Let me see. Where's the diagram? No. It's like right here. Where'd you go? Where'd you go? There it is. Yeah. For now, we're just literally going to be like, when this thing receives the final bit, just close the connection. Like, there's no more handshake. So we're kind of doing like a halfway UDP TCP. And again, the simplifying assumption is like, we're doing all the states in depth up here. And we know that there's a bunch of like logic. There's a bunch of like detail we have to add to like properly close a connection. And we're kind of just saying like, to send bare minimum one call, which is our goal from the beginning, to be able to send a call over the internet and establish a connection, send bytes, make sure they arrive. We can do that with some sanity checks and then like a simple close. We don't have to have like, because we're not trying to send multiple connections back and forth and build this like super complex thing. I think that's the quickest way for us to move deeper, like go deep instead of wide. And then what we can do is come back and be like, all right, let's build this second chunk later. So it's just like I'll make it not a bonus, it's a to-do. These are like later PRs, essentially. Speaking of PRs, we should also commit, because we've done a lot of stuff. We've all been in this one file. So state machine defined. Good stuff. Nice, 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 nice. I guess we don't need any of this anymore. Look how garbage this was compared to before. Yikes. Ugly. Get rid of it. Got it. So we got X. What happens if we run this, just out of curiosity? Sec, let me close door. Someone's cutting. Good call. Twitch recognized I was trying to talk and then told me to unmute. Stop being silly. So now we have to define the packet, basically. Now we're getting into kind of like a little bit deeper on the design. So we've designed the handshake. We need to define the packet, which is already defined for us. Shouldn't be hard. How do these differ? IPv4 versus IPv6. IPv6 looks simpler. Looks simpler. So much spam. Spam! Oh my goodness. No. 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 Holy. Wikipedia chill. So I'm trying to see the difference here first, just to understand that. Yeah, IPv4. So what was wrong with it? I think it's just the size. Yeah, it's less router or less header. Multicasting. Yep. So we can do some nifty stuff. But let's get this up here. Well, this is purely for addressing. So what we want is we just want IPv6. IPv6. I think we just want the header format. Traffic class field. Okay, so what do we got? I don't think traffic class even matters. Let's just see. It's just like priority. A flow label. I don't know what that is. I don't think any of this matters. Yeah, it's for routers. So there's a lot of like router specific stuff in here, which makes sense. We're not doing routing, we're just doing data transfer. Very simple. We are routing, we're just doing one-to-one. What is next header? I think this indicates TCP. Like it's saying, well, what's the data type that we're sending? It's probably it's like UDP, TCP. I don't know if it matters. It seems like these are just like a lot of just buffer. Like, okay, basically version, we don't care, don't care, don't care. This we care about, payload length. Oh, that's cool. This is neat. There's a hop limit. So like, if a packet is being forwarded a bunch of times, we just say like, nope, this has been hopped too many times. We don't care about it, but that's pretty cool. This is super cool. Okay, so we care about three things: payload, source, destination. So what do we got? I just want to get the exact amounts. It should define the header length pretty clearly. I mean, it's defined here, I just don't like adding numbers. So 32, yeah. So 32. 64. And then 128, 256 plus 64. Technically speaking, I can make an even smaller packet by removing all the zeros if I want to be smart, I want to be clever. I'm hesitant. I think that's a bad design decision because if I want to add more in the future, I have to like refactor everything. So I think that's kind of garbage. Yeah, so I'm going to revoke that idea. I think that's dumb. But we've got 128, this 32. What even is that again? Feels weird. Yeah, that's it, 320. It's kind of weird. 320 bits. Yeah, I mean, like, let's not violate that, though. That's pretty clear. So, all right, let's start programming. Let's just jump right into Python. Think like, how do we codify this? Well, I can tell you one thing. I don't want to be thinking about bit offsetting. So I'm going to write a helper class to do this. Definitely don't want to be in each of these subfunctions being like, oh, which bit is the thing that does the thing and the stuff. That just sucks. Let's actually put this outside because this could be used by multiple classes. IPv6 packet. I don't think this has to be an object. Let's chill. We don't have to be out of the way here. Basically, we care about three things. We care about payload size. We care about the payload. Literally payload. We care about that. Yeah, source and dest. Let's put an E here. Yeah. So I'm trying to think of how we're gonna do this. Basically, we're defining a packet. I'm gonna do a bit string, obviously, because it has to be binary, zeros and ones. We're gonna take in some nice fields though, and then we're gonna make it a bit string. We've also got to do that for, what is it? So take in the bit string, and we have to do this for a TCP packet. Like, I don't quite know how they're going to connect, but I know they're separate. Yeah, I mean, this ends up being the exact same thing. The payload's going to literally be the string, the bit string of the TCP packet. Yeah. Yeah, and so it's important to note that the payload size of the TCP packet the payload of the TCP packet and the IP packet are different because of they're completely different structs. But I think they both have send and receive, like a receiving IP and a send IP. Let's see here. I don't know if they actually do that. I don't think they do, no. TCP must. It's literally a routing. It's literally a routing packet. So it should have, I think they already define it in here, of course, as they should. Yeah. It doesn't have the IP number. Yeah, okay. Yeah, so IP has this. And we're using IPv6, but then TCP doesn't have that information. It has a bunch of different shit. It's kind of cool. Yeah, and I see that Copilot even knows that it's ports. So it's so aware of like what a TCP packet definition is that it used ports instead of IP. I think the only things here that we've been specifying are ACK, sequence. I'm trying to think of how to make this a bit simpler. Well, actually, I didn't know if we need the IPv6 definition then. Because the TCP packet, no, so IP packets are what are sent. They contain a data payload. This payload happens to be TCP in this implementation. It could be UDP. So technically this is correct. Let's just call it data. That's the correct term. I don't think anyone else calls it payload. The payload is technically the whole thing, like anything you're sending. Yeah. Cool. I think that's the only things we care about. We have these fields, they're going to be encoded into bits. So what we're going to do is each of these will have 2 bits. Now we need to somehow do Python bit strings. I need to see which library to use for this. Bit string. So we'll be doing it as, I think from ints. So you can do it as binary. first. I think this is the thing we'll use. Also, let's just see how to plug these in. 'Cause I think it's 3 o'clock my time now. I gotta hop off soon. But I want to get a little bit more done here. Okay, wait. Pip 3 install. Silly. 1 sec. Pip install Bitstream. Nice. Easy money. Let's just try running and seeing like how chaotic it is right now too. Let's fix some errors quick. I think it's supposed to take self, right? Because it's yeah. Let's clean this up a little. It's going to infinitely hang. So we should do check for syn packet. We could return a payload just to make this exit. We have to implement all these like low level nice. Both of these sending synac. We're just forcing these to move forward. Yeah, I mean, all these cause it to freeze, which makes sense. Cool. So we've got all our mock stuff going on here. Receive payload. Cool. So received payload from client. Seems like it just keeps waiting here. So one process closed, we can see this one. This process is still running. Oh, received payload. Oh, it's because they don't return. Is that why? Does it have to explicitly return or something? Send data. Yeah. Okay, cool. Basically, we have some of these calls running through. That's what I wanted. And now what else do we need to get it to? We're gonna have this TCP packet that we'll be passing around. We're gonna pass in data, sequence ACK to bits. We're gonna use a bit string. Just throw that in quick. Basically, I wanna spend like 5 minutes getting this as close to a checkoff point as I can, so that we'll probably have one more stream where it's like just iron out the drivers and like drill in, but at least we won't be doing like handshake logic. We're gonna be like, no, just like bitwise stuff and drivers. So up here, let's try using this actually, just see. Not string, bit string. It's just this. You should just be able to use that. Let's debug it, see what happens. Cool. What happens if we pass in a string? Let's look at the definition. Yep. So what happens if I do something like because I'm trying to think if we even need a library here. We could just use bit shifting operations, and we could basically specify sequence, seek ACK, and then just like shift the number of bits we want. I think that might be the way to go, actually. That might be the simplest way. And what we do is we just initialize I don't know, just like header. So we need to decide on like our packet size. So we're just gonna basically do So it's just binary, all zeros. Actually, I'm curious how if this works. Is that how it works in Python? Can you do that? It's kind of gnarly. We'll see. Z-fill. I'm gonna shift by 1. Let's just try this. I guess we need to make this a 1 for it to count, right? Otherwise it's kind of silly. Because now shifting to the left should make it a 2. Yeah, cool. Okay, I think that works. So I think the way to do this, we still need to do padding correctly. So that's the part. We've got multiprocessing working. We basically need to just, and we have a pretty good understanding now of how to break both IP6 and TCP down into packets with fields. We know the fields. We know we have to set the fields. So I think the next stream is going to be very low level, like basically bitwise work to write, I guess what would you call it? The IP layer, I suppose. So like if we go back to our the OSI networking model, right? I think we're below the transfer level now. Like we've done TCP, we're implementing TCP. I think we're getting down into networking layer now, where we're gonna do IP and like, yeah, basically writing a driver, a Wi-Fi driver. So I think in the next time, yeah, we're gonna do 2 things. We're gonna write the IP layer, and we're gonna write a Wi-Fi driver that connects with the hardware. I think that's the next logical chunk. And then the final, well, I mean, this could keep blowing up. We'll see how long it takes, but I imagine there's at least a couple streams. We will do a hardware stream, which might blow up into 2 if I suck with hardware. And then the networking and data link, which will be next stream, that seems pretty achievable in a few hours because we have our packets, we encode them as binary. And then we're going to write those onto the file system in /dev/proc. We're gonna have a process for reading packets, reading binary. So it's basically just writing this level, this abstraction level here for bit operations, which will be fun because like I don't think people work with bits a lot. And then we're gonna write a driver that takes a packet. So just read packets from list, find next packet to send, and send a packet, and then delete it. So it'll read the file system. We can write this out actually as like a next step. Next time. Logic to encode packets in binary. Write packets to dev proc 1 through 5. We're going to write them to the process file system, or write them to our file system in the process directory. And then we're going to write a simple driver to read packets broadcast over Wi-Fi bit by bit. We're going to do Morse code driver device. So we're going to broadcast over a physical device bit by bit. That's what we'll do next. And then we'll eventually build the hardware. Cool. Well, for those that were in and out of the stream throughout the time, thanks for dropping in. I will post what we've got so far, but yeah, we're making some good progress. Maybe I'll do a quick git commit. Got this one thick main file. Nice. Good stuff. All right, well, thanks for tuning in. And yeah, let's get at it next time. Maybe in a week. I'm doing a race next week in Tahoe, California. And so 32 miles, mainly high elevation. It's probably going to crush me, but it would be fun to try and do a stream the next morning. If I'm like able to talk, we will see. Yeah. All right. Peace.